Hello, everyone. My name is Tao Mei. I'm from AI Research of JD.com. Today, I'm very glad to be invited to this workshop of language and vision with applications to video understanding. So today, I will talk about the vision and the language from perception to creation. So you can see from this slide, there are two bird images in this slide. And actually, the left one is captured by the human, and the right one is actually generated by the machine. So you can see that today we will talk about how we can perceive from the image to generate the language, and on the other side, how can we create the image based on the language. Here is today's outline. First, we will talk about the technical landscape of vision and language, especially from vision to language and from language to vision. And then we will talk about some recent representative works about this topic. And later, I will introduce some real-world applications for the possible practitioners. In the past 5 years, our researchers have made impressive progress in both image captioning and video captioning. So from the left side, you can see, for example, in the year of 2015, the system can output a group of zebras standing in the field for this given image. The sentence is pretty good, and the verb of standing is also correct, but not that accurate. Later, in 2016 and 2017, the sentence is much improved to a group of zebra grazing on the grass or group of zebra grazing in the field. The action of grazing is more precise, and the description is mainly relevant to the setting objects. Last year, the system can be further upgraded, and more contextual information, such as rainbow and sky, could be described in the sentence. Similar, in the video captioning, on the right-hand side, you can see a captioning system cannot even differentiate men and women in the early stage for this challenging task. Because the video is blurry due to the raining, since the year of 2017, the gender of the person in the video could be correctly predicted. And last year, the context information about the rain could be described in the sentence. So here we show the technical landscape of the vision to language. The year of 2015 is actually a very beginning in image captioning. Before that, the mainstream of captioning is template-based method in image domain. The basic idea is to detect the objects or actions in the image and integrate those words into the predefined sentence templates, such as subjective, verb, and objective, SVO. At that time, most of the image captioning dataset are already ready to use, such as Flickr 20K and MS Coco. In the year of 2015, deep captioning models are first presented. The common design is to employ a convolutional neural network as an image encoder to produce image representations, and then exploit a decoder of LSTM to generate the sentence. The attention mechanism is also proposed at that year, which locates the most relevant spatial regions when predicting each word. After that, the area of image captioning is growing very fast. So you can see researchers came up with a series of innovative algorithms, such as augmenting image features with semantic attributes or visual relationship, predicting novel objects through leveraging unpaired training data, and performing high order or infinity order multimodal interactions from image captioning. Moreover, there are also emerging applications which involve vision to text. For example, captioning is integrated into an online chatbot first in the year of 2016. And also an AI created poetry is published in 2017 in China. And then you can see in 2018, we utilize captioning to produce the product description at JD.com. The starting point of captioning in video domain is also in the year of 2015. Then researchers start to exploit temporal attention, embedding attributes to further improve the video captioning. It is also worthy mention that in 2016, we released MSR VTT video captioning dataset, which has been widely used in this domain and already downloaded by more than 100 groups worldwide. The most recent work is to apply the short Fourier transformation across all the frame level features along the temporal dimension to fuse all the frame level features to video level representations and further enhance the video captioning. Next, I will summarize those tech representative works in details. The mainstream of modern image captioning follows the structure of CNN encoder plus LSTM decoder. Specifically, given the image, we can extract image features through multiple ways. We could directly take the output of the fully connected layers as image features, or we could incorporate high-level semantic attributes into image features, or we could perform attention mechanism to measure the contribution of different image regions, or we could extract the region level features and further explore the object relation or image hierarchy on the region level features. Then we fit the image features into the LSTM to generate the sentence, one word at each time step. In the training stage, the next word is generated based on the previous ground truth words, while during testing, the model uses the previously generated words to predict the next word. In order to bridge the mismatch between training and testing, reinforcement learning could be used. The ultimate goal is to maximize the reward function, such as the CEDA or the omitero in this task. Following the mainstream, one research trend of image captioning is to take the advantage of visual relationship between the objects and explore such relation to enhance the image encoder for captioning. The basic idea is to model the more comprehensive information or contextual information for image representation. The relation could be on both semantic and spatial levels. The semantic relation contains more than, for example, 20 types, such as in or eating, while the spatial relationship contains 11 types, such as inside, cover, and so on. The target is to integrate the connections into image encoder to produce relation-aware region-level representations and make the representation more powerful. Then, the valid question is how to model the relationship and how to integrate the relationship into the captioning. In ECCV 2018, so we devised a structure named the Graph Convolutional Neural Network plus long LSTM, long short-term memory LSTM. We named GCN LSTM. Specifically, we use the faster RCN to detect a set of salient image features. Next, the semantic and the spatial graphs are built with directional edge on the detected regions, where the vertex represents each region and the edge denotes the semantic spatial relationship in between. The GCN is then employed to contextually encode the regions with visual relationship. After that, the learned relation-aware region-level features from each kind of graph are fed into the one individual attention LSTM decoder for sentence generation. In the inference stage, we adopt a late fusion scheme to linearly fuse the results from the two decoders. We showcase a few image examples with the constructed semantic and spatial graphs, human annotated ground truth sentences, and the sentence generated by 3 different approaches. For instance, compared to the same sentence with a cake in the sentences generated by the approach LSTM and the approach up-down for the first image. Eating a cake in our GCN LSTM shows the image content more comprehensively. This is because the semantic graph can actually encode the detected relation eating into the features for enhancing the sentence generation. To further use the image features with more power, we propose the hierarchical parsing in the previous ICCV. The HIP actually can integrate the image hierarchy into the image decoder. Technically, an image decomposes into a set of regions, and some of the regions are resolved into the final one. Each region then regresses to an instance, for example, foreground of the region. Such process naturally builds a hierarchical tree. A tree LSTM network can be then used to interpret the hierarchical structure and enhance all the instance level, region level, and image level features. The HIP structure is pluggable to any neural captioning models. When taking a close look on existing CNN plus RNN captioning model, we found most of them capitalize on the convolutional attention module to trigger the multimodal interaction for image captioning. However, such attention module inherently exploits only the first order features interaction and is lacking in efficiency. Thus, in this year's CVPR, we introduced a unified X-linear attention block, which fully uses the bilinear pooling to selectively capitalize on visual information or perform multimodal reasoning. Technically, X-linear attention block simultaneously exploits both the spatial and the channel-wise bilinear attention distributions to capture the second order interactions between the single modal or multimodal features. Higher and even infinity order feature interactions could be modeled through stacking the multiple X-linear attention blocks and equipping the blocks with exponential linear unit in a parameter-free fashion. Furthermore, we present X-linear attention networks, which can integrate X-linear attention blocks into image decoder, encoder, and the sentence decoder of image captioning model to leverage high-order intra- and intermodal interactions. We also submitted the run of Xline to online COCO testing server. In terms of all the evaluation metrics, Xline leads to the performance boost against other captioning systems. The source code of our Xline have been released on the GitHub. You are welcome to use. The current achievement of image and video captioning techniques heavily rely on the requirements of large quantity of annotated image and video sentence pairs for neutral model learning, which is actually cost expensive and impractical in real-world applications. Therefore, we recently released a new large-scale video language pre-training dataset, and all of the video sentence pairs are automatically harvested from 100 million web pages. Based on this dataset, we host a new challenge which aims to boost the research on the emerging tasks of visual language pre-training for video captioning. If you are interested, you can check out the link on this page. Next, I will turn to discuss the generation problem from language to vision. There are two main streams of image generation based on the language inputs. The bottom line shows the single object synthesis, which has been very successful in the past years. Human eyes cannot even tell the difference between the real and the fake images. However, multiple object generation is a totally different story. From the top row, they are still far from mature. There have been many techniques developed for multi-object scene generation. From the very beginning, text is directly used for generation, sometimes with attention mechanism. To increase the visual quality, external constraints have been introduced through the years, such as the temporal dependency, semantic maps, scene graph, layout, and the relationship among the objects. Take the language to video generation, for example. The advancement is relatively large considering the visual quality and the temporal consistency. From the very beginning, the GIFs generation, the digit, and human motions. In general, there are two critical issues in video generation. The first one is smooth temporal coherence across video, and the other one is the semantic consistency between the captions and the generated video. With the technical development of the GAN, the resolutions of the generated video keep increasing from the 128 plus 128 to 512 times 512, and even more. The visual quality is also improved for practical applications such as virtual try-on. But still, generating a video from the language is still very challenging. Another example is the language to multiple object image generation, which also achieves substantial progress. We can see a clear path going from irregular object shape, structure, and layout. More pleasant results start to come out by applying a more structured language input. For example, a scene graph. The information conveyed by a complex sentence can often be more explicitly representative as a scene graph. Since the scene graph is more powerful, structured representation for both image and language, generating multi-object image with complicated semantic information can be much more easier. However, there's still a long way to go. The works on the multi-object image generation heavily suffer from two fundamental problems: the messy layout and object distortion. Johnson proposed a proxy-based method for multi-object image generation, while the scene graph is used as the proxy for generation. However, this method still suffers from heavy object distortion and a weird layout. To further simplify the difficulty, Hahn and Haynes further introduced the scene layouts as a proxy, but the layout only highlights each single object while ignoring the relationship among the different objects. Therefore, the results are unsatisfactory and often looks unreal. In our recent work, we highlight the function of relationship for multi-object image generation. The same object pair, for example, man and a board, could show different object shapes, scene layouts, and appearance under the different relationship. Thus, we propose three modules to inject the relationship on object shapes, scene layouts, and appearance respectively. First, the objects and their relationship are jointly adopted for object mask generation. The second, a relationship-guided spatial constraint module is proposed to generate multi-object layouts. And last, we propose a scene graph discriminator to make sure the generated image is consistent in both object and relationship. In the past 5 years, language has evolved from single text to captions and to a paragraph. And the vision domain also changed from the single object to multi-object, organized in a specific scene, and even to a hierarchical structure of constituent objects and instances that depicts a thorough visual understanding. In the near future, there are several main trends. Better language representations are being exploited in the NLP domain. For example, the scene graph, parsing tree, entities, and the relationship. Moreover, complex scene graph is another trend, since it is still far from mature. A video generation will prevail in the near future. So far, the research focus is on the nouns and the adjective in a sentence. In the future, the verbs will also be considered, especially in the video generation. The last, the research community starts to pay more attention on the vision language pre-training, which aims to transfer the multimodal knowledge from the rich resource pre-training tasks to a series of limited resource downstream tasks such as VQA, cross-modal retrieval, and image captioning. Here I show some applications in the real world, which shows how we can apply the vision and language techniques into the real world applications. So you can see that at JD.com, there are hundreds of million SKU or product images. So using these techniques from the vision and language, so you can see that we can teach the machine to produce the sentence which can describe the specific products. So you can see that given this products image about this window break, so you can see that we can actually produce a very natural sentence to describe this product. And this is another example. We can use the first, we designed the first AI robot, which can write a customized poem for given gift to a specific person. And we use these techniques to automatically produce tens of thousands poems for specific gifts. So this is another example about the machine-generated contents. You can see that given a specific products image, we can actually produce a personalized sentence to describe to these products. A few years ago, Microsoft designed a chatbot named Xiaoais, in China named Xiaobing. The Xiaoais actually combine the multimodal techniques from the NLP, computer vision, to enable the multiple term dialogue between the human and the machine. So you can see that the Xiaoais can actually empower the over 5 million users to create poems and also the multiple term dialogues. They even published a book using the name of Xiaoais. Okay, so this end of this talk by poetry generated by the system. So this system is actually a paper from the ACM Multimedia 2018 from Microsoft. So you can see that given this picture, the machine can actually generate a very beautiful English poem. I hope you can enjoy the poetry. Thank you.